Hi, welcome to Elasticity. Today we are going to take a fairly close look at what is meant by stress. You have probably seen this in your strength of materials classes and other things, but today we are going to take a look and figure out what exactly we mean and how this is represented in terms of a matrix. Item 1. Contact forces are caused by other bodies pushing, pulling or dragging this body through a common surface. So imagine that I have two bodies and they are contacting this way. That causes normal forces, that causes shear forces. So you can see that one hand is either pushing, pulling or dragging the other hand. Okay, so that's the origin of contact forces and we want to make this in a very careful way. Tension or compression gives rise to what is called normal stress. Normal does not mean common, it means perpendicular. So imagine two bodies, I cut one of them and I am moving them back and forth. Okay, so this is, if I want to see what is the effect of this, I have made one part disappear and I have replaced it with a force. The normal stress, average normal stress, is the normal force per unit area on the exposed surface. That's what normal stress means. Normal force per unit area on exposed surface. And if it is pulling, that is if it's pointing towards, if it's pointing away from the surface, it's positive. And if it's pointing towards the surface, it's negative. That is our common sign convention. Sliding gives rise to shear stress. So if two portions of the body or if two bodies have the tendency to slide with respect to each other, then they will give rise to shear stresses. And this is tangential force per unit area on exposed surface. So what matters to us is this idea of force intensity, not force itself, but force intensity. I mean, we all have an intuitive idea, right? It is not just how much force we are applying, but over what area it is spread. That's what really matters to figuring out whether something is going to fail or not. Okay, so that's what really occurs. Let's look at an example. I have a roller bearing. You know what a roller bearing is, right? It's two surfaces which contact each other. The contact area is 1 millimeter squared. The bearing presses on the surface with 4,000 newtons, and the coefficient of friction is 0.2. What are the normal and shear stresses? Are the question. So let's look at this thing. So there's the bearing, and there's the roller on top, and the roller is getting squeezed onto the surface. So you can see it is pushing on the surface, not pulling on it. So normal force will be minus 4,000. Why is it minus 4,000? Because it's pushing on it and not pulling. Shear force is 800 newtons. How did I get that? It is 4,000 times 0.2. Area of contact is 1 millimeter squared. So you divide normal force divided by area will give you 4,000, and please watch the units. It is megapascals. Newton per millimeter squared is megapascal. And shear stress, typical notation is tau or sigma Tn. We will talk about the notation in a short time. Is 800 megapascals, which is normal force times coefficient of friction divided by area. Okay, so you get the idea of what is meant by normal stress and shear stress, right? Very good. The thing to remember when you are doing notations for this is what is there on the screen, which is face the force. What it means is that our force notation, our stress notation will have two subscripts, not one subscript. The first subscript represents which phase we are talking about, and the second subscript represents which force we are talking about. For example, here is a body. You can see something that looks like a potato. We usually typically draw this, and in fact we have a technical name for it, and it's called a continuum potato. Okay, and there's a point somewhere inside it. There is no meaning to talking about what is the stress on the point, because stress has to do with surfaces, contact forces. So you got to say which surface. Okay, so here's my axis x, y and z. So first up is a surface which is cut perpendicular to the x-axis. You can see the nose or normal of the surface in red, and that's the normal to the surface. I can do a cut. Instead of cutting that way, I can cut along the y axis through the same point, and now the normal is pointing in the y direction, and I can cut through the z axis on the same thing, and you will see the normal is pointing in the z direction. So how much force per unit area I have depends upon which way I cut it. So let us say, for example, I cut it perpendicular to the x direction, and there is the normal. Now let's say I have some force per unit area perpendicular to it. This will be referred to as sigma xx. The first x is the phase, the second x is the force. So if you remember phase, the force, it's easy. The first x refers to the normal to the phase. The second x refers to the direction of the force. So if I do the other way, this way, can you see the phase is still the x phase, so it is still called sigma x. The force is in the y direction, so it is called sigma xy. So sigma xy, phase the force, x phase, y force. So if I put sigma zx, it will be z phase, x force. That's how it works. Okay, and this is important, so please memorize this in your head. It is a very easy mnemonic. It's called phase the force. Very good. So now we want to look at this in more detail. So like what we did on the surface of this thing, when the body deforms, portions of the body exert forces on each other due to the tendency of pushing, pulling, or sliding or dragging. We talked about this. So when the body gets squeezed together, like what I showed you, it will create normal forces, and when a body kind of goes sideways, it will create shear forces. So if you shear the body, slide it like a pack of cards, the individual layers of the card will start shearing each other. So we are going to call these things are called internal contact forces, and this is what governs what fields. So we are going to pick a point P, cut a body with a plane parallel to x-axis through P. So there you can see the point P, and it has been cut in a plane parallel to perpendicular to the x-axis, not parallel to it. There's the plane perpendicular to the x-axis. Expose the normal, and then the force on this face will have three components: fxx, fxy, fxz. The first x refers to the normal or nose or the face of this thing. Okay. The second refers to the direction of the force. So fxx is x normal, x face, x normal, y direction, x normal x direction, x normal y direction, x normal z direction. Now stress will be defined as force over area in the limit as the area shrinks to 0. So the force will also decrease. Okay. Sigma yx will be limit force over area fxy divided by a. That's our general expression. I'm sorry, that should have been sigma xy, sigma xz. Okay, so it is the limit of the force divided by area in the appropriate direction. Okay, we'll continue this. Now we are really going to look at inside the body what happens. There is the point. I'm going to take the point out there so that you can see what happens. So I'm going to draw. That's the x face, because its normal, its nose is perpendicular, is along the x direction. That's the y face, its nose is perpendicular to the y direction. There's the z face, its nose is perpendicular to the z direction. The problem is all of them are passing through the same point, and it's going to get very messy. So what I'm going to do is move the point to the corner like this for simplicity of representation. Actually what it is that the planes are all extended, but you can just see what happens. There are the three faces. You can see the three faces, right? On each of the faces there are forces. So this is the force per unit area on the x face, and it has three components: sigma xx, x phase x force, x phase y force, x phase z force. So remember, it is force per unit area. Okay, so that is sigma xx I, sigma xy j plus sigma xz k. So this has three components. The other two will have similar things. So there is a force on the y plane, sigma yx, y phase x force, y phase y force, y phase z force, z phase x force, z phase y force, z phase z force. Okay, per unit area, all of them. So if you look at all of them, you can write them in a nice matrix. Each column corresponds to the force on a particular phase. So you can see Tx, which is sigma xxi plus sigma xyj plus sigma xzk is the first row, first column. Ty, which is sigma, that is this phase, the force on the y phase is the second column, and the force on the z phase is the third column. So each of them represent the force per unit area on each of the phases. This is called the stress matrix in Cartesian coordinates, because we are using Cartesian basis. Okay, and it's very easy for you to read off. You can plot what it is. If you look at the subscripts, it will tell you what it is. So if you look at y, this is y phase, y force. Zy is z phase, y force. Okay, yz is y phase, z force, like that. Okay, we are going to assume that when bodies contact each other, they are only able to push, pull or slide. They are not able to twist or torque the surface. Okay, so this is a key thing, and there is these things are called couple stresses, and there are theories which have them. They are called couple stress theories. We are not going to talk about them. In this particular case, we are assuming, for our purpose, we are assuming that when phases contact each other, they cannot transmit torques per unit area. Those kinds of bodies are called ordinary or simple continua. Okay. So when we do these forces, we also have the equivalent of Newton's third law. So I have a body which I have shown it as a lump, and I showed you a cut. So if I imagine there is a normal to the cut, there is the force, and it has two components: n phase, n force, n phase, tangent force. Right? The corresponding thing on the other side have to be minus n phase minus n force, minus n phase minus t force. Can you see how it is drawn? Newton's law says the net force on this phase and the net force on that phase have to be equal and opposite. That is Newton's third law. So what does it mean? So Fnn, n phase n force, is F dot n over A, must be equal to minus F dotted with minus n over A. If you substitute that, you will see that's true. Same thing with the tangent force. So what it means is that the n force on the n phase, or the n phase n force, must be equal to the minus n phase minus n force. The n phase t force must be equal to the minus n phase t force. So this should be the other way around. Okay, so they have to be equal and opposite. The way it is that the stress components are the same. The direction of them are automatically picked by the normals. And you are used to seeing little cubes in which stresses are drawn. I want you to realize that that's not a free body diagram of a small piece. Okay, that's an entirely different thing. So I want you to understand this point. So please remember, when you look at a little stress cube and you draw forces on it, that's not a free body diagram. You'll have to do that in a separate way. So let me show you what I mean. Here is my area, and here is the cut that I have made, and on each of them I have shown you the forces: sigma yx, sigma yy, sigma xy, sigma xx. The corresponding equal and opposite forces are shown there, and Newton's third law will tell you that this force and that force will be the same, this force and that force will be the same, this force and that force will be the same, this force and that force will be the same. You know what I mean? This and this, this and that. But it's very inconvenient to draw it like this. So what we will do is, we will just move it to these two faces. These are not the forces on these two faces. This is the outside face, no? But for us to be able to draw all this setup, including Newton's second law, it's very messy. I mean, Newton's third law, it's very messy. So we will just move it here for convenience. They actually used to be here, but we are just moving it there. Can you see that? and we are drawing it to be equal and opposite. But this is not due to Newton's second law, it is due to Newton's third law, and this force was really out here and this force was really out there. So please remember, when you draw this kind of a stress cube, it is not a free body diagram, it's just a convenient way of representing forces. Thank you very much.